Okay, good morning. Thank you for joining us today for our environmental remediation at Chalk River Laboratories, Tackling Complexity with Care webinar. First off, CNL respectfully acknowledges that the CRL site is located on the unceded and unsurrendered territory of the Algonquin Anishinaabe Nation. We recognize and appreciate their historical connection to this land, and as the customary keepers and defenders of the Ottawa River watershed and its tributaries. We also recognize and appreciate the contributions that all First Nations, Métis, and Inuit peoples have made and continue to make in shaping this land we now know as Canada. We acknowledge, respect, and seek to better understand the unique Indigenous history, rights, and title on the lands where we work. Now, this is a little bit different than other webinars that you've watched. So this is going to be a re-recording of our webinar on this topic. There were some recording issues on the live one, so we are going to try our best to do the exact same thing in this re-record. We're going to have the exact same content. We're going to have the exact same questions asked, and we will try our very best to answer the questions the exact same. So we'll go from there. During today's webinar, you'll be hearing from Jen Hamilton, Project Manager, Environmental Remediation at CRL, who'll be sharing information on some recent environmental remediation work. And then after the slides are done, we will do the questions. And like I said, there'll be the exact same questions that were asked during the live webinar. So Jen, over to you.
Thanks very much, Mike. Good morning. As Mike mentioned, my name's Jen Hamilton. I've been in the nuclear industry for 16 years, with most of those years involved in providing technical support to CNL's research reactors and operating nuclear labs. In the last 4 years, I joined the part of CNL responsible for decommissioning our older facilities and remediating the lands affected by our activities over the past 80 years. Through this session today, I'll describe some environmental remediation projects at the Chalk River Laboratories site of Canadian Nuclear Labs. And I hope that by sharing these projects with you, I will illustrate the careful process that we follow here at CNL to tackle some pretty complex problems. For example, in this picture, you see the team drilling a borehole. This is part of getting samples of the soils below to gather information about the site. And I'll touch more on this later. But first, let's get situated. While CNL has laboratories and project sites across Canada, my projects are focused on environmental restoration at Chalk River Laboratories, shown here in Ontario. Our purpose is advancing nuclear science and technology for a clean and secure world. And part of our mission is to restore and protect Canada's environment by reducing and effectively managing nuclear liabilities. While research conducted at national nuclear sites across the country have brought tremendous benefits to Canadians, these historical activities have also generated radioactive waste that must be addressed. But let's take a look at the first step in our remediation process. Step 1 is environmental site assessment. It's used for gathering information and characterizing the site to build a comprehensive picture of the nature, extent, and variability of the contamination or lack of contamination, and it includes the initial development of the conceptual site model. Our example here is the electrical yard landfill, and we start by understanding the site's history. From 1944 to in the 1950s, this was part of the Dawson City work camp, and that was the part of the site that was a construction camp during the time that the Chalk River Labs site was being built, starting in 1944. The full camp contained several buildings, including a hospital, mess hall, and kitchen, a store, and several dormitories. Within the electrical yard landfill site boundaries, there were several work camp storage buildings, buried water and sewer lines, a sewage chlorinator, and a sewage outfall pipe. Through 1960 to about 1972, it was used as an inactive burning dump. So after the work camp shut down, many of the camp buildings were dragged to the riverbank and burned. The site was operated as an inactive burning landfill from 1960 to 1962, meaning that non-radiological materials were deposited and burned at the landfill. Landfill waste material was deposited down the slopes leading to the riverbank. Through the 1970s to the 2000s, it was used for electrical equipment and salt storage. So after the landfill closure, 1972, the electrical yard landfill was covered with sand and gravel fill, and it was used for surface storage of electrical service materials, a firefighting test facility, and a salt storage shed. So historical site configurations are shown in this figure. The salt storage shed was removed in 2007, the firefighting training buildings were removed in 2016, and the electrical equipment storage building was removed in 2016. And we stopped storing electrical equipment at the electrical yard landfill in 2016, and the site has been vacant since that time. From these photos and all those other records, we assemble the history of the site, and this allows us to work out potential concerns. Once we identify our areas of interest, areas of potential environmental concern, which we'll show on the next slide, we carry out field investigations, taking samples, monitoring water movement, and looking for the presence of contaminants as a result of these past activities. So we've listed out our areas of potential environmental concern here. And next, we develop an initial conceptual site model for electrical yard landfill. And we've developed that based on the information gathered during those previous environmental investigations. The site model is shown here. We still had some questions to answer though, and we wanted to confirm the lateral and vertical extent of the waste in the landfill, the groundwater table elevation, the effect of potentially contaminated activities from the past on our soil quality, our groundwater, and our surface water today. So we map out our investigation. We determine the extents of the landfill waste to the north and the south. Another goal, as I mentioned, was to confirm the waste thickness in key locations, and then estimate the volume of different types of waste. We also wanted to characterize the groundwater quality at the site down gradient of the landfill. And to show you how we do some of that, I'll share some pictures of another site at Chalk River. So here at Reactor Pit 1, we carried out a field sampling campaign. Drilling allows us to collect soil samples from various depths below the surface. We log what we observe and send portions of the soil out for lab analysis, quantifying the contaminants. This adds important detail to our understanding of the current conditions of the site. Still showing Reactor Pit 1 site here, we have an aerial view of sampling that we did this summer. You can see we have a sampling tent set up not far from the drilling locations. They can be long, hot days in the summer, but the resulting data can make our remediation efforts much more focused and efficient, so well worth it. Gathering information from around our project site, we also drilled to gather geotechnical information, and we installed wells for groundwater sampling. All of this information helps us to better understand the site and plan for that remediation. So once we have the details of the site, we map out our data. If we come back to our electrical yard landfill example, I can report that in spring 2024, we completed our characterization there to answer those lingering questions so that we can plan our environmental remediation with confidence and take appropriate waste management decisions. 16 boreholes were drilled and 3 test pits were excavated. 1 additional monitoring well was installed, and soil and groundwater samples were taken for laboratory analysis. Here's our, next up is our stratigraphic west to east cross section of the area. With this, we can plan our excavation to access and remove the waste. But with a bit more imaging, we can develop an even better model of the waste and create our dig plan. So let me show you a bit of that. For this area, we've used laser scanning and associated processing software to enhance visualization. We collected our data set using terrestrial laser scanners, a tripod-based, and mobile mapping, so the backpack style, as you can see on one of our colleagues. The data starts as a point cloud. It's what's generated from the laser scanning. Moving or temporary objects and noise in the data are removed. The area boundary is defined. Data is segmented so that ground, trees, or objects can be hidden or moved. Next comes a technique called ground meshing. By isolating the ground and drawing triangles between points, a bit of an interpolation between points, we can create a 3D surface without holes. Next, the mesh surface is extruded using a separate software, and now our model has volume. The provided dig plan map is projected and textured onto the mesh. We get a great visual this way. So that's our initial integration. The mesh can be integrated with the remaining point cloud data to visualize how foliage or other objects will obstruct our plan. We can even model our excavation, visualizing the earth, trees, and the objects that will be removed during this excavation, and we can estimate the volume of waste that we'll need to remove. Once we have this model, we can create some great visualizations. We have a video clip to show you. So this is the electrical yard landfill. As I mentioned before, it's a site of a former landfill for non-radiological waste that was identified by CNL as a priority for environmental remediation. The site is located along the southeast portion of the Chalk River Laboratories built-up area, bordering on the Ottawa River. It's covered with grassy vegetation on the flat upper section and trees along the slope section leading to the riverbank to the east. Previous environmental characterization programs at Electrical Yard Landfill identified soil and groundwater impacts by primarily non-radiological contaminants associated with the former landfill. A remedial options evaluation recommended that waste material from the landfill footprint be excavated to address environmental impacts. So when we investigate a site like this one, we have several considerations. We know that the site is currently considered industrial use. It may be intended for parkland use in the future. It's adjacent to a water body. Potable groundwater is not used within 500 meters of the site. The site soil is considered to be coarse-grained, and the site is currently vacant with no plans for development in the near future. As our next step is planning the removal of the waste, videos like this can help us visualize some of the hazards that we'll encounter, and so we can plan for those. We can talk about ways to protect the river, keeping heavy equipment away from the shore, and minimizing our disturbance of the silt. We can plan around times of spawning fish and nesting birds, protecting species around us. So let's look at an area where we've completed a remediation. Due to its proximity to the built-up campus part of CRL, this southern portion of the Foundation Road landfill was identified to have high redevelopment potential to help fulfill future business needs at Chalk River. This can be a driver to decide priority for which areas get remediated. We're not inclined to develop on areas that have been relatively undisturbed. Rather, we'd prefer to keep new facilities close to existing infrastructure and already in disturbed areas. So the purpose of the project was to restore the south portion of the Foundation Road landfill to predetermined land use criteria in preparation for site redevelopment. After final characterization of the area in 2022, we had a good understanding of various buried waste materials and contaminated soil present. The materials had varying degrees of radiological and non-radiological impacts, with non-radiological contaminants driving the need for remediation. Waste segregation and sorting was selected as the most sustainable approach to minimize the generation of both waste and contaminated soils with low levels of radiation, and waste and soil contaminated with non-radiological contaminants, including heavy metals, polycyclic aromatic hydrocarbons, and dioxins and furans. Bulk materials excavated with heavy equipment were screened for radiological contamination in bulk with a Nuvia Gamma excavation monitor, or GEM, to verify the appropriate disposition. So you see in this bucket on the right is being monitored by that GEM monitor. So once we're done the waste excavation, the materials are sorted into what can be recycled as fill or disposed of as waste through appropriate waste streams. We can record the depth of our dig, as you can see in the photo on the left. And on the right, you see the site as it was on the final day of remediation. If you think it looks like a construction site, that's probably fair. As I mentioned, this area was remediated to be ready for land redevelopment. This is in contrast to what our restoration will be for the electrical yard landfill, where we don't plan to use the site for redevelopment. So now let's check out some approaches when we have some difficult waste to remove. At one of our waste management areas, we have a legacy calandria, or reactor vessel, that needs to be removed. There are internal hazards, including radiological hazards present, and we're working on special remote tooling, both for the internal investigation, like this image taken during a visual inspection on the left, and special equipment for the segmentation and packaging of the waste. On the top right, this was the calandria in the winter of 1975 after being stored partially buried before it was fully covered. These photos helped us to confirm the orientation in the ground and the processes we could use to recover it. It's a good contrast between the disposal requirements from then to those today. The top left shows one of those 16 damaged fuel positions from the NRX accident. So some interesting item to tackle. As you see in this graphic, We're doing detailed planning for the retrieval of the component, its size reduction, and its packaging. We have a ventilated segmentation shelter and an environmental protection shelter that will be around the whole area. The proposed site layout for the segmentation fieldwork is shown here. We have an area for the control room for some remote operated equipment. We have a waste packaging area, support and maintenance areas, and a shipping and receiving area. We've even practiced our techniques using a mock-up. So we'll show the mock-up video there. In doing this mock-up, our reactor segmentation project had several questions on the approach: soil management, how to uncover the vessel. We built a full-scale half model, so that's about 9 feet tall and would be about 10 feet in diameter if it were whole. But we wanted to be able to set up cameras to be able to see the inside. We have some fuel channels represented, 3 sets of 7, to give us an idea of the ability of the cutting tools to access with representative spacing of those fuel channels. It showed that the tubes were quite flimsy, so we didn't need to invest in developing a specialized tool for cutting those tubes. One of the things that this can tell us is where we can buy tools that are readily available on the market. It will also help us to identify those special operations where we'll need to have some tools specially designed. Some of these components are 3-inch thick pieces of aluminum. And once we worked through this mock-up, we were able to focus on our procurement efforts in the right areas to develop special tools for that kind of cutting. This way we could organize our effort to really address the right problems and not all the problems. Because there's a lot of contamination in the component, we know that there will be a lot of debris that we'll need to clean up. We wanted to determine if the robot will have sufficient maneuverability to support the cleanup. And then at the end of our video here, you'll get to see a robot holding a long shop vac, a snow brush, and just vacuuming up the dust. So some low-tech solutions for some interesting problems, but we got to test them out here in this mock-up. So remediation can be a complex and invasive process. It's not always feasible to tackle promptly. We collaborate with Canadian university students to research management methods in the interim, or even ways to constrain the movement of contaminants to stop them from interacting with receptors being humans, plants, and animals, in the future. The nitrate plant was built in 1953, and it was designed to condense and dispose of dissolved waste fission products, which contained high concentrations of ammonium nitrate. Waste was directed into an infiltration pit. After a year of operation, the plant was closed due to spills and equipment malfunction. The nitrate plant spills resulted in estimated releases with very large quantities of strontium-90. Through our groundwater monitoring program, we monitored the progress of the leading edge of contaminated groundwater over the years. On the right, you can see a figure showing the progress of that leading edge. As the leading edge advanced toward the nearby body of water, we developed a capture system was designed to slow it down. On the next slide, we show the wall and curtain. It was installed in 1998, and I'll tell you a few of the key components of the wall and curtain that make it so cool. Though I should mention that the figure shows the plume of contamination traveling towards the lower left of the figure, and the graphic of the wall and curtain is, if you can imagine, rotated from its installed position. So we're looking at it where the groundwater flow enters in. We see here there is a cutoff wall, which hydraulically separates the plume and the treatment from the down gradient swamp. The reactive curtain itself is a clinotylite, or clino, which can be pretty much thought of as a molecular sieve. The curtain drain is a perforated pipe with the curtain and maintains a uniform head across the clino, and the capture zone is controlled by the elevation of the drain outlet. Our treated effluent travels by discharge pipe to the lower Bass Creek and eventually lower Bass Lake. So it's been operating for 26 years and it's still functioning, but we're working with the University of Waterloo, their Groundwater Geochemistry and Remediation Research Group, to collaborate to estimate how many more years do we have left for the treatment at that wall and curtain. Our estimation requires field sampling, coring into the reactive material, and modeling. So some great collaborations with other folks. And I'm happy to answer any questions about any of the activities that we've got going on here at Chalk River Labs.
Okay, thank you. Great presentation, Jen. We will now get to our Q&A. So the first question is, what are the advantages of using laser scanning for environmental remediation compared to traditional surveying methods?
Thanks. Yeah, so the laser scanning actually captures a huge amount of data very quickly and is extremely precise. So within a few millimeters, we can have the location of every bump, tree, rock, or piece of infrastructure. We can also map those to monuments on the site so that we can overlay our other mapping or radiological scanning onto our images so that we get a really detailed and really reliable picture of the site as it is today.
And how can laser scanning data be used to track changes in contamination levels over time in ongoing remediation efforts?
So having the data stored and having it geo-referenced allow us to be able to take future images like a snapshot in time. Similarly with radiological surveys, so we can overlay those radiological survey data on top of our imagery, and we can see how it's changed from one snapshot day to the next. And I can't hear you, Mike. Thanks.
Even in the re-record, I forget to hit the mute button. Have PFAS or PFAS compounds been added to the landfill remediation criteria?
Yeah, so PFAS would probably be a contaminant, especially if we have a firefighting training area. It's often used in a firefighting foam. So that was definitely one of the contaminants of interest, of concern at the electrical yard landfill. So where there's a contaminant of potential concern, then we'll look for those and test for those. When we were doing our sampling campaign, we had to take special efforts of what our crew was wearing because PFAS is actually used in a lot of water repellent outerwear, sometimes reflective vests and things like that. So we had to make sure that our sampling people were wearing clothing that would not inadvertently contaminate our soil samples and give us false positives. So there's some interesting concerns with PFAS.
Okay, thank you. Are there any specific tools used alongside laser scanning for data analysis in environmental remediation projects?
So we do have some software modeling tools that we would use to help us look at the, say, the volumes or the locations of some of the contaminants. And that survey, radiological surveys overlaid on top of our imagery can really help us to know where the hazards are going to be. And even looking at where towers are or overhead hazards or buried piping if we have them in drawings that we can overlay into our models. So all of those things can kind of be meshed together if we have the data.
Okay, thank you. Next question. The video showing the disassembly of the NRX calandria mockup showed some rough handling of the pressure tubes. How will the disassembly of the real radioactive tubes be accomplished?
So excellent question. And that's some of the things we were learning and the mock-up demonstrated really well. So understanding how things were going to react when we were in there with cutting tools, allowing our operators to gain practice and allowing us to evaluate whether that's something that we want to have as a method in the future or if we want to modify it so that there's a more gentle approach. But these are things that are best figured out with a little bit of a practice run, and that mock-up gave us lots of excellent information to plan for the real deal.
Okay. Next one. How effective is the using of laser scanning for environmental? Sorry, let me start again. How effective is using laser scanning for environmental remediation compared to other methods?
So it's really just a method for data gathering. Remediation is not really helping us with the remediation itself. It's just allowing us to get some extra information. And anytime we have a good image, that will help us to help develop our plans. one thing we find a lot of, if there's difficulty in finding records of how things have been, then it's more difficult to piece together that historical picture. But where we can put together those great pictures, then we can see where the contamination is. We can plan for all those hazards that might be in our way, and also help convey to any of our regulators or folks who are interested in how we plan on making our approach. We can use a model to actually show people what we're envisioning.
Okay, thank you. Next question. What important lessons, if any, have been learned from other CNL remediation projects in the past that you and your team applied to your own work?
I think one really good one that we've seen is around engaging a lot of the various groups. So it is a huge undertaking, and there are a lot of specialized groups across CNL, people who have a deeper understanding of maybe species at risk, or other processes, maybe chemical processes that might be at play subsurface. So engaging those other resources and engaging them early so that we can plan to incorporate their feedback, those are always great things to do, and just making sure that we're talking to the right people early enough on so that their input can be incorporated, which is kind of like a project management advice in general. Just engage your stakeholders early, and and you'll have fewer risks to manage later.
All right. Are there any biological methods like phytoremediation used to address contamination at affected CNL sites?
So I don't believe we're using any phytoremediation at the moment, but it's very interesting future, I think. And I've seen a lot of interesting conference papers and topics covering phytoremediation, especially if you are able to capitalize on some local pre-existing, like indigenous bacteria, so that they're already in an area that they are comfortable, and would like to explore that some more. So definitely something that's on the table, and something that we'd be probably happy to collaborate with the university student perhaps on looking at what might work for our site.
All right, thank you. Um, what's the criteria used in prioritizing various contaminated sites at CRL?
Yeah, that's a great question, because we do have various areas across site. It's a big site, and of the ones that have had potentially contaminating activities, we look at how stable the contaminants are, how close they are to areas that we want to be using, um, whether we want to redevelop the area. We have a document on our website that we can probably link to. It's called the Overview Decommissioning and Cleanup Plan, and that talks about a lot of those different factors, and goes into the various management units across the Chalk River site, detailing what our potential plans are for each of those areas, and talks about those areas that we do want to redevelop and the areas that we'd rather leave green.
Okay, thank you. Will CNL be looking to the marketplace to advance any of these remediation projects?
Yeah, so we do have a great supply chain, and so we want to work with where it makes sense to work with local suppliers and folks in the area who have the expertise, then to contract out some of our work. We have the responsibility to make sure that it gets done right, and where it makes sense and is great, then we'll work with external vendors to help us out.
Okay, does CNL collaborate with other research institutions or organizations to advance remediation technologies?
Yeah, we're parts of some groups. Conferences and things like that are a great opportunity to share information and look at what other people in the industry are doing. And then also these collaborations like that one I highlighted with the University of Waterloo really helps to engage academia to see what solutions are being chewed on next, and how those might apply for our site in solving some of our real problems here.
Okay, thank you. Only a couple more. What are some of the biggest challenges facing remediation at CRL?
Well, one thing I tried to demonstrate here was the complexity of the site. Um, we have some interesting challenges, and a lot of the environmental remediation specialists that I work with comment on how interesting the site is because of its complexity, because of the variability of the contaminants present. Um, we have industrial hazards like a typical industrial site would, and then overlaying on that the nuclear research aspects that we've had in the history here at the Chalk River site, it just makes it that much more interesting and more complex. So very interesting things like that make it a challenge here at Chalk River.
All right. Okay, last question. How will CNL address the cleanup of Waste Management Area C?
So that's probably a good one to look at our ODCP for specifics on there. A lot of our areas, if they're still operating, then we don't have the immediate plans. And where there is a long runway to remediation, it might be best to look at what are the technologies available at the time when we are getting closer to remediation. So check the ODCP for that one.
Okay. All right, that's it for questions. Jen, great presentation, very informative. Thanks for answering all the follow-up questions. So this version will be on YouTube. And for anyone that has any follow-up questions or any ideas on any future webinars or anything like that, please email us at ermstakeholder@cnl.ca. Thank you again, Jen, and thanks for tuning in. Okay, thanks everybody. Have a good day.